Today I'm going to teach you how to work with vector components. Let's think about how we would find the magnitude of our x and y components. Well, if you look at how we've drawn these vectors, you can see here that there's a right triangle, okay? And this right triangle has the x and y component as the legs and the vector a as the hypotenuse, okay? And so we can actually use a little bit of trigonometry to figure out the magnitude of our x and y components. And normally you'll be given an angle here, the angle between the x-axis and the vector, okay? So let's say we want to find the magnitude of our x component first. Well, we're going to use cosine, and the reason for that is because the cosine of our angle here is going to be equal to adjacent over hypotenuse, right? And as you can see, in this case, the adjacent leg to the angle is the x component. So we put the magnitude of the x component there. And the hypotenuse is going to be the vector a. So we'll put the magnitude of vector a there. And now we can multiply each side by a and rearrange this to get that the magnitude of the x component is going to be equal to the magnitude of vector a multiplied by cosine of the angle. Okay. Now, what if we wanted to find the y component of vector a? Well, we do something similar, but this time we'll use sine, because the sine of the angle is going to be equal to the opposite leg divided by the hypotenuse. And so in this case, that would be the magnitude of the y component over the magnitude of the vector a. Okay, and so again, we would rearrange it and we would get the magnitude of the y component is equal to the magnitude of vector a times sine of the angle. Okay, so it's worth mentioning that we have these nice equations here for how to find the x and y component, but we need to be careful because this only really works when the angle theta is the angle between the x-axis and the vector. So the angle between them. Because if you used, let's say, instead of the angle between the x-axis and the vector, you used the angle between the y-axis and the vector. So that would be this angle here, and let's call that phi. Let's say you use this angle phi here, okay? Well, in this case, right, you could still find the same x component of the vector a and the y component of vector a, but our equations would look a little different. And the reason for that is here, cosine of the angle phi would be the adjacent leg would be the y component, and that would be over the hypotenuse, which is still vector a. And so the y component would now be found by multiplying the magnitude of the vector a by cosine of the angle. And if we did sine of phi, then it would be the x component over the vector a's magnitude. So now, as you can see, the equations look a little different, okay? And so most likely in your class or in your textbook, you were given this set of equations to go off of, and that is assuming that this angle that you have is the one between the x-axis and the vector, and not the one between the y-axis and the vector, okay? So just keep that in mind. Make sure you understand this trigonometry so that you don't have to worry about making any mistakes just by blindly following an equation. Okay, so now I've drawn the two legs, which are the x and y components. Oh, sorry, made a little mistake here. Okay, and what if we knew the magnitude of these two components, but wanted to find the actual vector and the angle? Well, we can also do that because we know the Pythagorean theorem. So in this case, let's say this is let's just call that vector a. And so if we wanted to find the magnitude of vector a, we would just have to do the square root of the magnitude of vector A's x component squared plus the magnitude of the y component squared, okay? And you would get the magnitude of vector A. Now, we've been working with just the magnitudes, but of course, vectors have a direction as well. And so that direction is going to be specified by this angle. And we can also find that angle using trigonometry. And this time we're going to use tangent, because the tangent of the angle, which is what we're trying to find, is opposite over adjacent, which would be in this case vector A's y component over vector A's x component, okay? And therefore, we can say that the angle is going to be equal to the inverse tangent of the y component over the x component, okay? So now you have these two equations to figure out the vector's magnitude and direction when you just have the x and the y component. All right, so let's do an example here. Here we have a velocity vector. The velocity vector has a magnitude of 40 meters per second and a direction of 30 degrees above the horizontal. And so here, our angle is the angle between the x-axis and the vector. So we can actually use the equation that we derived earlier that looked like this. To find our x and y components. Okay, and so first let's do the x component. So the magnitude of our x component of the velocity vector is going to be the magnitude of the velocity vector multiplied by cosine of the angle. And so that would just be 40 meters per second times cosine of 30 degrees, which is root 3 over 2. And so the magnitude of the x component is going to be 20 root 3 meters per second. Okay. As for the velocity vector's y component, it's going to be the magnitude of the velocity vector multiplied by sine of the angle. And so now this would be that right there. All right, so here we have the answers that we just got. And you'll notice that we actually don't have the vector symbol above our velocity variable. And the reason for that is because we found the magnitude of the x and y component. So what would we have to do if we wanted to turn this into a vector? Well, we would have to specify direction, okay? So one way we could do that is we could say 20 root 3 meters per second to the right. Or if we define the rightwards direction as positive and the leftwards direction as negative, we could actually just write this as positive 20 root 3, or I guess we don't really need the positive sign. And this would be the vector because the positive 20 root 3 indicates that this is going to the right. Likewise, if we wanted to turn the y component into a vector instead of just giving the magnitude, we could say 20 meters per second upward, or we could just leave this as positive, assuming that we've defined upwards as positive and downwards as the negative direction. Okay. The reason why I mentioned this is because obviously not all of our vectors are going to be in the first quadrant, meaning there's a positive x and positive y component. A vector could be in the second, third, or fourth quadrant, right? And so let's do another example here real quick where there is a vector in the third quadrant and see how that changes things. Okay, so here we have a displacement vector with a magnitude of 10 meters, and the angle between the x-axis and the vector is 60 degrees. Now, I'll talk about this a little bit later, but in actuality, this vector, the direction would have to be described as being 240 degrees above the horizontal or 120 degrees below the horizontal, okay? But for the purpose of our problem, all we need to know is that the angle between the x-axis and the vector is 60 degrees. So now we're going to go ahead and find the x component, which is going to be that, and then the y component, which is going to be that, of our displacement vector. But we're going to find the magnitudes like we did earlier before we actually think about what the vector quantity is. That will be including the direction. And so here, the x component of the displacement vector would be the magnitude of the displacement vector times cosine of the angle. And so that would be 10 meters times cosine of 60 would be 1/2. And so the magnitude of the x component is going to be 5 meters. And for the magnitude of the y component, it would be this here, where we do 10 meters times sine of 60, which is √3/2. And this would give us 5√3 as our answer, okay? Now, this time, okay, and once again, we're going to define left as negative, right as positive, up as positive, down as negative. If we wanted to write these as a vector, okay, we could very simply, for the x direction, since it's going left, we could write 5 meters left, or since left is the negative direction, we could just write this as -5 meters. And what this would tell us is that the displacement vector's x component has a magnitude of 5 meters and goes in the leftwards direction. Likewise, since downwards is the negative direction, the y component of the displacement is going to be -5√3 meters. So now we're going to take a look at how to use the x and y components to find the magnitude of the vector and the angle, so the direction of our vector, okay? So we're just going to go back to this page here and pretend we don't know that the velocity vector was 40 meters per second and that the angle or the direction of that vector is 30 degrees above the horizontal, okay? We can also erase all of this. Earlier, we established that we can use the Pythagorean theorem. So the magnitude of the vector is going to be the square root of the magnitude of the x component squared plus the magnitude of the y component squared. So in this case, in order to find the velocity vector, we can square 20√3 meters per second and add it to 20 meters per second squared and take the square root of that. And we will find, this should be a magnitude of the velocity. And we'll find that the magnitude of our velocity vector is 40 meters per second. And we actually know this to be true based on what we did earlier. And so this is great. Now, in order to make this a vector, of course, we need to find the direction, okay? And earlier we said that the inverse tangent of the y component divided by the x component would give us the angle, okay? And so we can do that here and say the inverse tangent of 20 meters per second divided by 20√3 meters per second and plug this into a calculator, and you would indeed get 30 degrees, which is consistent with what we did earlier. And so in this case, by using the Pythagorean theorem and the inverse tangent equation that we derived earlier, we find that the resultant vector, or I guess not the resultant vector, but the vector that we had the components of is actually 40 meters per second, 30 degrees above the horizontal. Let's do the same thing for the second problem that we had done, where the vector is actually in the third quadrant. Here we found that the x component is equal to negative 5 meters, the negative indicating that the x component is going to the left, and then the y component is negative 5 root 3 meters because it's going downward, okay? And so we can do something similar to find our vector here, okay? And of course, we want to find the direction as well. So what we're going to do is the magnitude of our displacement vector is going to be equal to the x component's magnitude squared plus the y component's magnitude squared. And we take the square root of that. And so this would be 5 meters squared plus 5 root 3 meters squared. And notice how I didn't put the negative sign. I guess putting the negative sign wouldn't matter because we're squaring these numbers and that would make them positive anyways. But since we're just working with the magnitudes and not necessarily the vector with the direction, we can just write the positive version of our x and y components here, okay? And you would indeed get 10 meters for your magnitude. And then we're going to do, sorry, let me rewrite that. We're trying to find the angle, and we know that that's going to be the inverse tangent of the y component and the x component, or the magnitudes of the y component and x component. And that would give us this here. Sorry. Okay. And this would result in getting 60 degrees, okay? Now, we're right in that this is indeed 60 degrees, the angle between the x-axis and our vector. However, it would be incorrect for us to say that the displacement vector is 10 meters, 60 degrees above the horizontal. That would be incorrect because 60 degrees above the horizontal would be, this is from the positive x-axis and 60 degrees. So then the direction would be completely off because we're in the other direction down here in the third quadrant. So although the angle between the x-axis and the vector is 60 degrees, we need to account for the angle from here all the way to here. And that angle is 180 degrees. And we'll add 60 degrees to that. And so our answer would have to be then 10 meters, 240 degrees above the horizontal. Because the horizontal starts at the positive x-axis, and then we go counterclockwise until we reach the direction that we want for our vector, okay? Now, another thing we could do is we could measure below the horizontal, okay? And so in that case, from here to here would be 90 degrees, and so then we know that to get to the 60 degree mark here, it would be another 30 degrees. And so that would be 10 meters, 120 degrees below the horizontal. Okay. Now, going clockwise, like I said, is the positive direction when we measure angles. So this could also be written as 10 meters with a direction or with an angle of 240 degrees. Or here it would be the displacement is 10 meters and the angle is negative 120 degrees because going clockwise from the positive x-axis is a negative angle.